Okay, welcome to my office. Let me walk around. So, my name is Glenn Wheeler. I'm an Australian mathematician, currently an Alexander von Humboldt Research Fellow at the Otto von Guericke Universität in Magdeburg, and welcome to my office. So, I know that the resolution on my camera isn't very good, but I've written something on the board here which is supposed to explain a little bit about this exciting series of lectures that I'm going to give at the Korean Institute for Advanced Study. So this will be on one-dimensional geometric evolution equations, which I've simply called flows and curves. So when we have a curve in space, there are certain things that we can do to analyze the structure. And one of the things which I like to do is to start flowing and bending and changing the curve based on some rigorous geometric evolution law. And in this situation, if we have a curve which is immersed like this, then this evolution equation will tell me at every point on the curve where should the point move. Here is a red direction here, this one might be one evolution equation. This green vector is coming out of the board, and this blue vector is going back into the board. So let me go and pick you up, and we can look at this, what I've written here, a bit more precisely. Okay. So here's our immersed curve, and these are the three examples of a geometric evolution along the curve. So the curve is supposed to evolve towards some ideal state, and mathematically we write it like this. So I call the initial data, that's this guy here, I called him gamma 0. He's a map from the unit circle into Rn. Sometimes it will be in the plane when n is equal to 2, and other times it won't matter. And then the flow with initial data gamma 0 is given by this one parameter family, gamma, so here's our circle S, this is a parameter domain, 0 to capital T. Capital T is just a positive number, time, it's the maximal time in this case of existence for the flow, and it has image in Rn. Okay. And along the flow we prescribe its time evolution, so this is the time evolution of gamma, this is going to be a vector, as the following velocity vector, which is a function of gamma. And this velocity vector is going to be some sort of differential operator, and there are two basic examples of curvature flows which I'd like to focus on in this lecture series, and that is when we take this velocity vector to be the second derivative with respect to arc length, S is arc length, of the position vector gamma. Now this is nothing more than the curvature vector, so this is the very, very well-known curve shortening flow, where we take the curve gamma and we shorten its length as fast as possible in the function space L2. Okay. Now, another well-known evolution for this curve, so another well-known choice for V, is the following. So we take the curvature, this is just the curvature, and then we compute its normal Laplacian. So don't be too scared about this guy, I'll explain him in detail in the lectures. Basically, we keep taking derivatives with respect to arc length of the curve and project them back onto the normal bundle of gamma. This is not too complicated, and this guy is called the curve diffusion flow. Now, one thing both of these flows have in common is that they both decrease length. The first one decreases length in L2 as fast as possible, and the second one decreases length in h minus 1 as fast as possible. Now this means that the first guy is second order, he's a second order differential operator, it's quasi-linear, so it's a bit complicated, but it's second order, so we have things like the maximum principle. The other flow, this curve diffusion flow here, he's fourth order. He depends on fourth derivatives of the position vector. So we won't have things like the maximum principle available. But the second guy, he preserves enclosed volumes. So if we look at this guy, this example here, and we think about the minimal surface which is trapped inside this curve, then we flow this curve by curve diffusion flow, the area of that minimal surface will remain constant along the flow, the signed area. So even though it may be a little bit more complicated, it has some some good properties, which I'll talk about in the lecture series. Now, in order to understand these guys, what I'm going to do is I have the following goals in mind. The first goal is to perform a classical and modern analysis of the curved shortening flow, this CSF here. Now this will involve talking about the solitons of the flow, so these are the special solutions of the flow, as well as which form models for the singularities along the flow. This was a key idea of Grayson. Well, I mean, he used this idea, I don't know if it was his idea or not, but we will talk about special solutions for the flow, as well as going through the classical literature. So this is the work of Gage and Hamilton, work of Huisken on distance comparison. So this first theorem of Hamilton and Gage shows that any convex planar curve shrinks to a round point under curve shortening flow. I'm going to go through this theorem in detail. Huisken gave a distance comparison principle for the evolving curves, which I'll go through in detail. And then Grayson dramatically improved the result of Gage and Hamilton. He actually proved that any embedded planar curve under curve shortening flow will shrink to a round point. This is really quite impressive, and we'll talk at length about this. The proof is fairly technical and involves the classification of singularities, and quite recently, so this is where the modern part of modern curve shortening flow comes in. Quite recently, Andrews and Bryan provided an alternative proof for Grayson's theorem, and this will be this I'll also talk about. Okay, now it turns out that, as I alluded to before, there are whole families of curvature evolution equations, in particular for curves, which can be understood as gradient flows. So this is curved flows. So the second goal that I have in mind to talk about is to explain some sort of abstract framework within which we can cast all of these evolution equations which I would like to study. So this is called curved flows as gradient flows of geometric functionals. So in this case, in these two model cases, the geometric functional is just the length of the curve. And in the one case we minimize the length in L2, and in the second case we minimize the length in H minus 1. But this is not the only choice. We could also minimize the L2 norm of the curvature squared. This gives the elastic flow, which has also been very well studied. We could also minimize all kinds of other functionals. We could mix the functionals together and minimize a combination of them. We could minimize something like a Helfrich type functional, where we take the difference between the curvature vector and some other vector. And these all give well-motivated, interesting flows, which I would like to cast in some general framework and then study. Particular cases which I would like to examine in the second part of the lecture series are the curved diffusion flow, and for this I'll go through the work of Chuk, Kuvert and Schätzler. In fact, they work on several flows. I'll go through all of their work. Elliott and Garketh, who provided some preliminary results, and then some work of myself, which is an improvement, and some geometric inequalities which give some interesting information about the flow. Then I'll move on to a generalization of Chuk, Kuvert and Schätzler, which is recent work of myself, on the generalized Helfrich flow, which is a flow of a fairly complicated functional and gives you a fairly complicated velocity vector here, and it's also in high codimension, just like Chuk, Kuvert and Schätzler's earlier work, and this will probably take up the rest of the time for the lecture series. But if we have some time left, then I would love to speak on the affine curve lengthening flow, which is work of Ben Andrews, which is also a gradient flow, but is a gradient flow in affine geometry. And as a gradient flow in affine geometry, it is extremely singular, but very interesting. So this would be a great place to leave it. Hey, we'll have to stop.